Everybody, we're going to go ahead and get started. You will find your way into the University of Lowbrow Astronomers Monthly Meeting, November edition. And anyway, what is it? So I'm Charlie Nielsen, the president of the club. I think I have been forever pretty much. Can't get out of it. Anyway, here I am. We have a few other officers here. I think there's one in the Zoom audience, and we'll probably get some reports on that later. But as tradition would have it, we always have our guest speaker first in the event that some of you who really interested in that did want to stick around for a really enlightening and entertaining business meeting afterwards. So if you left in between, that would be fantastic. And our guest tonight is Professor Dragan Huterer, who some of us know because he is also one of the people that has brought us the group to the Michigan Math and Science Scholars up at Beach Mountain. So some of us have met him before. And he's also a theoretical cosmologist and astrophysicist with the U of M Physics Department. He earned his Bachelor of Science from Massachusetts Institute of Technology back in 1996 and his PhD from the University of Chicago in 2001. His research is in cosmology at the interface of theory and data. He uses measurements from telescopes on the ground and in space to better understand the makeup of the universe as well as its past, present, and future evolution. In the late 1990s, cosmologists discovered that the expansion of the universe is speeding up, not slowing down as expected. This discovery, honored with the Physics Nobel Prize in 2011, has generated waves in the field of cosmology and presents us with a grand mystery. What is the origin and nature of dark energy, the stuff that causes the accelerated expansion? Dragan will review the exciting new developments in this field, including hints for new physics lurking in the data and the upcoming ground and space telescopes dedicated to solving the dark energy mystery. He will also briefly discuss analyzing hints of new physics in the dark energy sector based on observations with the dark energy spectroscopic instrument known as DESI. So we're going to welcome Dragan, but let's hope that he doesn't go too fast for us.
I don't think you're trying to. Thank you for the introduction. And it's very good to see you all. First of all, Lowbrow Astronomers, thank you so much for hosting our MMSS, Michigan Math and Science Scholar students in the summer when they go to the mountain. That's really, it's a huge favor to us and to them. The class I teach every summer, except this summer I got quite ill, so I couldn't, my students had to pick up, finish the course, so I was in a hospital in France while this was all happening, what's going to happen and whether they're going to the mountain or not. I'd like to talk to you a little bit. About 3/4 are about dark energy. Background, what happened last 25, 30 years. The universe is doing some very strange things. I'm going to talk about that. And the last quarter, I'm going to talk about latest developments with a very exciting experiment called DESI, with which we at Michigan are involved. And lots of things are happening, including next week, there's going to be a major release of DESI data. Right, so actually, apologies. I know it's much better if I stick this in, so I'll get this going, no worries.
Can the Zoom audience hear us?
Probably not so far, but now. Now you should.
I think we need to go here.
Let's see, 1, 2, 3. Okay, so I think you can hear me better here. Okay, much better. And it's not booming too much, hopefully. Okay, like so. So let me see if I can reach with my stick here. Maybe I'll show some stuff on the screen. So I'll start, the history of all this starts not quite with ancient Greece, but at least 100 years ago, the question is, what are these objects? Of course, nowadays we know they're galaxies. And the interesting point in time was 1920 with a Curtis-Shapley debate. Two astronomers, Shapley and Curtis, debate is what are these, what they call spiral nebulae. Shapley said they're part of our galaxy, the Milky Way. Curtis said, no, they're separate island universes, how they call them. Curtis was correct. They are indeed what he called island universes, galaxies. So that was an interesting point in time, 1920, well before our times. It turns out this solidified, as I'm going to show illustration later, to a cosmologist, somebody who studies the universe, they're point particles. They're like a person in a lab studies some particle is maybe in a pool of water. For us, these are point particles. Each galaxy with 100 billion stars is just a point particle. So another very familiar event in astronomy, 1929, when Edwin Hubble discovers that the universe is expanding. Now, Hubble didn't give very much credit to Vesta Slipher, who was really essential in getting redshifts of those galaxies. But just to remind you that expanding galaxies receding from each other is not a special thing in the universe. Any expanding space has that feature. So here's expanding space of a raisin bread in the oven. And as bread grows, every raisin recedes from another raisin. And the farther away the two raisins are, the faster they're receding from each other. So this is called Hubble law. But Hubble law, you don't need to have it for the universe. You can have it for the raisin bread. And Hubble law implies that in expanding space, you will find the farther away something is for you, the faster it's receding from you. So this is the relation that Hubble found. And the slope of that relation, if you put a line and measure the slope, so you divide velocity by distance, that's called the Hubble constant. Okay. So now in this picture, velocity is relatively easy. And that was provided by Vesta Slipher, whom Hubble didn't credit very much. And then the distance is hard. And this is a little bit of a different story to which I won't go into right now, but the distances were obtained from Cepheid variable stars that pulsate, and from the frequency of their pulsation, you can figure out distance to that galaxy. So this is all pretty familiar story in astronomy. Here's blue shift, redshift. So this is what we're observing for essentially all the galaxies. They are redshifting away from us. Their spectral lines are shifted to the red. And this is one all-time favorite plot. It's a very famous plot directly from Edwin Hubble's 1929 paper. This is the distance and the velocity, but other than adding this blue text, I didn't do anything to it. And this is the slope that Hubble measured. Now, the completely crazy thing about this is that Hubble inferred the Hubble law, that there's a relation here, but the slope of this line is a factor of 7 wrong. The slope should be 7 times smaller. So today we know that the Hubble constant, the slope of this relation is 70 kilometers per second per megaparsec. That is to say, for each million parsecs, galaxy recedes 70 kilometers per second more. Hubble measured 500 for this number, way, way, way off. So that almost like if God whispered in his ear, hey, it's a line. Trust me, it's a line. Put a line through this. And he put a line, but the slope should have been more like this. So there was huge systematic errors in these measurements. Now, the interesting corollary of this is that the age of the universe is approximately 1 over h naught, 1 over this. So for this kind of Hubble constant, you get the normal age of the universe of 14 billion years. But if you stick in 500 here, you get age of the universe of 2 billion years. Now, what's the problem with age of the universe of 2 billion years? That it's been known for a while now that age of the Earth and the Sun is more like 4 and 5 billion years. So for a few decades after this, when this number was 500, cosmology was a science that predicted the age of the universe to be younger than the Earth. So cosmology had a very bad reputation in the 1930s, 40s, maybe 50s, because it was catastrophically wrong, all up until this number got fixed up. Then this number is very familiar to astronomers. For a long time, there was, to me, a rather tedious debate. Is it 50 or is it 100? One famous guy was claiming 50, another famous guy was 100. They were debating. When I was an undergrad, it converged to 70. So halfway in between. And now there's a very, very interesting coda to this, which I'm going to mention later on in my talk. I'm going to come back. So preserve this in memory, this number, 70 kilometers per second megaparsec. I'm going to come back to this in a bit later. But anyway, that story for the most part converged. And this Hubble law is, universe is expanding. That was a big time discovery. Now, in addition to expanding universe, what would you like to know? Now, in mathematics, you can show that if you talk about space, just space of any number of dimensions, including 3 dimensions, you have, this is 2-dimensional examples, you have flat space with 0 curvature like a sheet of paper in 2 dimensions. You can have positively curved space like a sphere or negatively curved space like a saddle. And you can show in mathematics, these are the only 3 possibilities. And you can wonder which one. Now, famous mathematician Carl Friedrich Gauss, he wondered about this. And he realized that if you measure the sums of angles in a triangle, only in a flat space will you find 180. You can check this on any sphere yourself. If you add up these three angles, they add up to more than 180. And likewise, these add up to less than 180. So Gauss actually climbed on a mountain peak in Germany and measured angles to two other mountain peaks. Then he went to the second one, measured the angle. Then he measured to the third one, he measured the angle. He tried to figure out if angles add up to 180. And I think he found they sort of do, but today we know he had no chance. You can go to three mountain peaks and do this. If you're going to check this for the universe, you need to be at one galaxy and do it, and then you have to move to another galaxy, obviously impossible. So you need galaxy type distances, not mountain to mountain type distances. So Gauss never had a chance, but his idea was in principle right. So, and obviously how we figure out what geometries we don't go to, we cannot ask our friends in another galaxy, hey, what angle do you measure? So this is a fundamental question you can ask, and I'll tell you immediately, this is the winner. This is the kind of space in 3D that we found, but about 20, 30 years ago, people were trying to do this, and it turns out that if you measure this the distance versus redshift, so redshift is a measure of how much light stretched from emission to us, and distance is distance. That relation, this is the area that Hubble covered in his Hubble law, so there's always a line here. But then these curves diverge depending on whether you have negatively curved space, what we call open universe, flat universe, or positively curved space. So the idea is to populate this with measurements and try to figure out which possibility we fall on. So I will jump immediately to tell you what we found, what people found. They agree with this case. However, they found that the curve looks unusual. That is to say, space is flat, but there seems to be something in our universe in addition to just matter. Okay, so anyway, the motivation, I hope that's clear. The motivation was to check out, hey, what's the geometry of space? So to measure distances to objects. And distance in astronomy is very hard to measure. My astronomy friends tell me, you know, things are not labeled with a distance. So type 1a supernovae, now they are pretty famous because of these discoveries. Objects, they are cases where presumably there's two stars and one accretes matter from another. And one of them eventually reaches the so-called Chandrasekhar mass limit, undergoes nuclear explosion, and this is a very bright explosion. One star is a fraction of luminosity of a whole galaxy that has 100 billion stars. And it turns out, by measuring this so-called light curve, the amount of light you receive from it, you can measure distance. It's a completely empirical relation. That is to say, it's a very much an astronomical thing. So here's a light curve. Yeah, you didn't see it. So I'm going to play this again. Light curve, the light from a supernova goes up and down, and this is versus time. So it's about 1 or 2 months. Over a period of a couple of months, light goes up and down. And you'll be able to see a supernova here somewhere. Let me play this again. So supernova right here. And you can see how bright it is. It becomes bright. And so by measuring the shape of this curve, and purely an empirical relation, empirical means it just happens to work, you can infer distance to these objects. The history, that's another talk, which I won't have time for, but for the history of supernova search is fascinating. They were known to be potential measurements of distance as far back as Fritz Zwicky, who is a famous Swiss-American astronomer. But the problem wasn't knowing that supernovae might be useful. The problem was actually guaranteeing that you look in the galaxy and find a supernova, because again, my astronomy friends tell me, if you point a telescope to a galaxy and wait, you have to wait like 50 years or something for a supernova to go off. So that proposal to Hubble Space Telescope will not be very successful, where you have to wait 50. So the thing they did is they found a way to look at many galaxies and guarantee that at least some of them will have supernova. And then when they do, you go back to it every few days, because remember, you have to cover up this about a month. So if you see one here that went off, you come back every few days to map this out. Like I said, that's a little bit of a different talk. I won't go into it too much, but the supernovae are nearly standard candles, another familiar thing to astronomers. This is my pedagogical example, kind of like cars' headlights at night. You don't know what kind of car it is, but if you have several of them, and if you're told it's the same kind of car, so the same type of supernova, then by measuring relative amount of lights, you can measure how far away. For example, if you have one that's bright and one that's dim, and if it's the same make of a car, then one is nearby, one is far away. So this is basically to say you measure flux. This is a little bit subtle. This is one of the two equations I'll have today. It's going to be on the test. Flux is luminosity divided by 4 pi distance squared. Flux is the thing you measure. Luminosity is the thing, how much power the object itself gives out. So flux you can measure. You can say my detector, I can detect some flux, but luminosity nobody knows. And then this is what you're hoping to know. But for supernovae, we sort of know that they are type 1a are nearly the same luminosity. That's like the same, nearly the same make of a car. See, if I know this thing is the same for all supernovae plus minus, then by measuring ratio of their fluxes, I can get the ratio of their distances. So that's the one and only important insight into how people use supernovae. This is a very famous thing in cosmology. Now it won the Nobel Prize, this kind of realization. But it was known, this was known to Zwicky already 70, 80 years ago. So people have done that. And this is what I said. You have to wait. Maybe this is 50 years, not 500 years. I'm not sure. But you have to wait a long time. So people have used the world's leading telescopes and spent a lot of time on the phone to convince agencies. And they did the analysis, and it resulted in this really major discovery in cosmology that was awarded with Nobel Prize in 2011. The discovery that there is dark energy in the universe. And so what was found is, this is another one of my favorite graphs because I used real data to make it. So each data, this is a distance as a function of redshift, except I took a logarithm like all good astronomers do. And so each data, this is real data. It's not something made up. Each data point is about 20 supernovae. If I plotted every single supernova, there would be a ton of points with big error bars. It'd be hard to follow. So I just binned it, I combined them. And so you can see that these are the possibilities that we try to check out: an open or flat or closed universe. These are the geometries of the universe. And neither one of them fits the data. Instead, the curve that fits the data is flat universe, but not with matter only. Flat universe with matter and something else. So it is a universe that accelerates, that decelerated in the past, accelerates now. So universe, I'm going to wave my hands, expanding slower and slower, and then speeds up. Speeds up kind of late. A few billion years ago, that's considered very late. And so this is the equivalent. Let me just kind of find this. So this picture, it would be like looking at a picture of the car, and it's dim. You're looking in time. It's dim, 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 dim. It's suddenly bright. Suddenly gets bright. What does it mean? That means the car sped up, right? It was dim and suddenly it got bright. So I really like that analogy because it's a very good analogy. That's exactly, we are not waiting in time, but we have different supernovae at different distances. And so the trend we observe is that distant ones are dimmer than we'd expect them to be. So that's the same as saying it was dim and then suddenly it got bright. So this was discovery. So again, this could be a whole other talk, details of this, but let me not talk about the details. There's some fine points about this picture I could discuss if anyone cares, but that led to the discovery. Statistically, this was significant in 1998 and 1999. And since then, it was completely cemented by other surveys that have nothing to do with supernovae, in fact. And they led to the discovery of a new thing that's not known what it is. We call it dark energy. My PhD advisor, Michael Turner at University of Chicago, called it dark energy. And he and I had, in fact, the first paper with words dark energy in it. But Mike, he gave it the name. It was an excellent name because it is energy in the universe and it's dark. Sounds kind of like dark matter, but it's not. I'm going to talk about it in a moment. So what is going on? What is dark energy? We don't know. What does it do? It makes the universe expand faster and faster. When? At late times. And it's smooth. Smooth means that there's as much of dark energy in this room per cubic whatever meter as in the solar system, as in the galaxy, as in the empty space. There's exactly the same amount, which is totally different from even dark matter, let alone normal matter, of which obviously there's much more here than, if you go outside out in the universe. So here's a little cartoon movie. Universe is expanding slower and slower. And then just when you think it's slower and slower, it starts to speed up in its expansion. And that speed up happened about 5 billion years ago. Now, dark energy and dark matter, I do realize, are similar words, easy to confuse, but the two things are totally different. Dark matter, here's how I think about dark matter. This is a cartoon. It's not a real image. Every time you see a galaxy, you think of a blob around it. This is what we call the dark matter halo. It's like a sphere of dark matter. It's more dense inside than as you go out. And dark matter is just some kind of particle, which we haven't detected yet, that clumps gravitationally via Newton's law and tends to dominate. It's more diffuse, and this is a picture of dark matter. Dark energy, totally smooth thing. I don't have a good picture for it. Smooth thing that fills space and kind of pushes things apart. There is not a lot of dark energy in this room, but that's because the universe is big. So if you average over all the empty space out there, you get a big effect, even though in a solar system or in this room, there's not a lot of it. I can tell you how much of it there is if you care, but it's not a lot. So facts about dark energy, I said it's smooth already. So this part, again, is very different than dark matter, which clumps. Dark energy does not clump. It pushes galaxies apart. This is the kind of weird thing. Its density is constant. Now, this is a weird thing, that density is constant, because if you think about, if I have a box of particles and I expand the box, that's my universe, I expand it, the energy is like mc squared of those particles. So the energy is the same, but I just increased the box. So the energy per volume, which is the density, goes down, right? The energy per volume, energy is the same, volume went up, energy per, density went down. So normally you expand density to go down. For dark energy, density is the same. So if I have a box, I have some energy, energy density, I double it. I have the same energy density, therefore I have more energy, right? Because the density is the same. So in a universe of dark energy, you get energy out of nothing. And that is actually allowed by the laws of physics, even though it doesn't make intuitive sense, but it is allowed. And I don't have a good analogy for that, but that's kind of the weird thing that happens with dark energy. Whether it's exactly constant or slightly off is at the forefront of measurements in cosmology. Only noticeable at recent times. Don't look for it in a very early universe. We don't think it's present there. This is the really important thing. It suppresses the growth of structure. If universe were 100% dark energy dominated throughout the history, there will be no galaxies at all, literally no galaxies. So to the extent that there was some dark matter and dark energy, the dark matter dominated in the past, there are galaxies, but the creation of galaxies is slowing down due to dark energy. And the universe is more, we could have this very nice conversation without dark energy. We don't know that it's necessary for anything in our lives or in the universe. So it's kind of like, why is it there? It's not necessary for any, not even just human life, but for anything in the universe. It doesn't make anything particularly better. What is dark energy is one of the forefront questions in physics. And I will tell you right now, we don't know. There are lots of ideas. It turns out that energy of empty space, which turns out to be non-zero, could be dark energy. So, electron and positron may pop up out of thin air and annihilate back. And this doesn't happen very often, but happens sometimes. So if you sum up this, which particle physicists have done in 1930s, you can get energy, but you get something like dark energy, except 10 to the 120 times more. Now, here I bother to write 10 to the 120. That's an incredible number. The number, this is 120 zeros. The number of protons in the universe is something like 10 to the 80, so 80 zeros. So this is completely unimaginably big number. So this vacuum energy could be dark energy, except it's too big by this much. So that implies two things. First of all, this is not a very good explanation. And even if you forget dark energy, why is this vacuum energy, is it zero? So people thought this is a crazy big number, but maybe it's zero, because zero is like a special number. It's a round number, right? Zero is zero. Turns out if this is the explanation, it's not zero, but it's very, very small compared to what you expect. This is called, this is maybe the most famous problem in all of physics. Maybe it's one of the top 3 in physics. Certainly in cosmology, it's the most famous problem. Extremely hard problem. I don't recommend to any of my students that they work on it. It's hopeless because the problem is too hard. People think, physicists think, that understanding this problem will only happen once there's a breakthrough, some kind of breakthrough like quantum mechanics, some kind of real breakthrough to understand why is vacuum energy. It's not zero, but it's certainly way less than it theoretically is. Okay, so that's the one mystery that's really famous. The other one is pretty famous also. It's called coincidence problem. Coincidence is, you go out in Ann Arbor and you notice everyone has, first 15 people had blue and maize colors. Wow, that's of course, if you knew you're at University of Michigan, it's a bit not so unusual, but otherwise you'd be, wow, that's a coincidence. So it's one of those guess what happened to me coincidences. And the coincidence goes like this. If you look as a function of time, the density or whatever energy in both matter and dark energy, remember I said matter density dilutes as the universe becomes bigger, but dark energy has that weird property that its energy is approximately constant. We're not sure if it's exactly constant or slightly off. Now, today, dark energy is 70%, dark matter is like 25%, or matter is 30%. So it's like 70 to 30%. But if you look at this scale is a huge number. So in the past, matter completely dominated. In the future, presumably dark energy will completely dominate. So the question is, why do we just happen to live at a very special time when dark energy to dark matter are 70 to 30? Like 1 to 1. It's one of those things, wow, guess what happened to me today? I went out and I saw something very unusual. So we went out, we saw something unusual. It's hard to put the probability on this, how unusual it is. It's one of those guess what happened to me. But a lot of people have worked over the past 20, 25 years making some models that would try to guarantee this, or even the notorious entropic principle, can we only live here? But we don't think that dark energy is necessary for anything having to do with our life. So that is a curiosity, and it's a mystery number 2, the second of the 2 mysteries. Why? My PhD advisor called it why now? Why do we just happen to live at a time when the 2 are comparable? What's dark energy again? I'm repeating myself a little bit on purpose is it vacuum energy? That energy that's okay, that's a standard model is vacuum energy, except theoretical explanation is completely wrong. Is it modification of Einstein's theory of gravity? This explanation goes as follows. That would be a huge thing to say Einstein was wrong. The theory of gravity isn't quite right. There's this addition that he didn't realize. And if you put in the addition, you get the effect of the accelerating universe. That really, people search for such departures in data, and we do too as well. It's a new fluid, we think, that fills up the universe. Well, basically, the short to all these bullet points is we're not so sure. But dark energy has there are several bizarre consequences, and I like these 2. One of them is guaranteed. So this is not an if, this is only a question of when. It turns out without dark energy, as you wait, say a few billion years, you see more and more galaxies because light from those distant galaxies finally had time to get to you. But in dark energy, something weird is happening. Universe is expanding so rapidly that faraway galaxies are running away from us faster than the speed of light. Now, you might say, how is that possible? Speed of light is a maximum speed. Well, speed of light is maximum speed. There was a fine print. Footnote in that chapter. It's only true in a lab, like in a small piece of space, like in this room. But it's not true because it turns out you can't even define the relative speed between you and a really far away galaxy. So formally, it can look that the galaxy is receding faster than the speed of light, even though it wouldn't be if you brought it to be near you. Okay, that fine print is not read very often. So it turns out those galaxies are effectively receding far from us. So there are fewer and fewer of them. So in fact, the sky will be empty in 100 billion years. I know that's a lot of years, but the sky will be empty because galaxies will have run away from us. Except for one that you all know about, Andromeda will have met we will have met our fate with Andromeda in a few billion years from now. But other than those local events, the sky will be empty. So that's a pretty interesting corollary. This doesn't happen without dark energy. Without dark energy, there's more and more and more galaxies that you can see as you wait. And the next one may or may not happen. It's not guaranteed, but it's completely crazy. It says that under certain circumstances, and I can tell you which. So this, depending on dark energy parameters, it doesn't happen in the standard model of dark energy with cosmological constant, but it would in slightly different models. We'll have what people call the big rip. That is to say that the expansion of the universe will become so rapid that galaxies, stars, planets, houses, and eventually atoms, and even the space itself will rip itself apart. Now, if you ask me what does it really mean, I don't have a good analogy. But mathematically, it's very clear. It's that the size of the universe, typical size, becomes infinite in finite time. Now, in physics, some big things become infinite in infinite time. So that can happen. Yes, it's infinite, but you have to wait infinite time. So don't worry about it too much. But if something becomes infinite in finite time, even if finite time is 100 billion years, that is a finite amount of time. So if you stick around for that long, this will happen. Again, this is guaranteed. This is a maybe, depending on the parameters that describe dark energy that we are trying to measure. And this one, yeah, I don't have a very good intuitive parallel, except it's such a, yeah, that's a statement. Infinite size in finite time, that means ripping apart of the space-time fabric itself. Okay, so that was my review of dark energy. Let me mention one more thing. Let me see if there are questions and we have time, and then I'll talk about one more final topic. But let me see if there are questions about dark energy, in fact, and take a breath here. Yes?
Is there any tie-in between dark energy and inflation that we think happened?
Yeah, you have an excellent question. Is there a connection between dark energy and inflation? Something I didn't explain, but you correctly inferred, is that dark energy looks a lot like whatever thing powered the period of inflation at early times. So after Big Bang, there was a period of rapid expansion that looks and acts exactly like dark energy. Yes, that's an immediate hint. Wow, these two things must be the same. The only problem is inflation happens at a time and energy scale. Dark energy happens billions of years after the Big Bang. Inflation is 10 to the minus 33 seconds after the Big Bang. So in much, much, much earlier time, higher energy. And this difference in times and energies makes it very hard to link them. So people have tried this a lot theoretically. It sure seems like a hint from the universe, hey, similar kind of thing happening again, but so much later that people don't know what to make of it. Was there another question on dark energy? Yes?
How do they know the discrepancy between the vacuum energy and the dark energy?
Yeah, so that's an excellent question. And thank you for asking it, because I went through it a little fast. So this is a result of a theoretical computation. Now you can say, who cares about theoretical computation? It's obviously wrong. Well, yes, it's wrong. But theoretical computation is based on quantum field theory, which is like extension of quantum mechanics. And quantum mechanics, as you know, is a gold-plated theory on the basis of which this computer and my cell phone and half of our economy, or whatever, 40% of economy, is based on quantum mechanics. Theory that was never falsified, and no experiment ever falsified quantum mechanics. It's, you know, a genius of a theory. QFT, quantum field theory, is an extension, also very successful. So this success story, it's not some random theory somebody made up. That success story in this case obviously gives a wrong answer. So that's what puzzles people. You know, why is it wrong here when it was right everywhere else? Nobody knows how to solve that. This is like the most famous and maybe the hardest problem in all of physics. Any other questions on dark energy? I'm doing well on time here. Okay, good. Yeah, and I don't want to go too fast at the same time either. I assume some of you have heard some of this background on dark energy, right? Maybe not all of you, but some of you. But maybe it doesn't hurt. And a lot of this story hasn't really changed over the past 10, 15 years. But my favorite, let me just say one more thing. When dark energy was discovered, it was a big shock. It was a shot heard around the world. It was a big surprise. And some people justifiably said, look, these supernovae, no offense to astronomers, they said, but it's an empirical relation. Empirical relation is, you know, this is bigger, therefore that's bigger. I just don't trust the supernova. I don't know. Those astronomers, they just go out and measure something. They have no control over this. Systematic errors, if you want to get on a pedestal, you mentioned systematic errors. So that was a legitimate thing, because who are you to guarantee that with your life if you're an astronomer, if you're a supernova astronomer, that something didn't break in this procedure. So about 5, 6, 7, maybe at most 10 years after, so in the early 2000s, we finally had data from cosmic microwave background and from what I'm going to talk about, baryon acoustic oscillations, from other pieces of cosmology. And at that point and today, even if you completely throw out type 1a supernovae and say, I don't believe any of this supernova stuff, I don't believe this light curve, this standard candle, I don't trust any of it, you still get a very, very confident answer for dark energy. In fact, I asked one of my graduate students a few years ago for fun to calculate the evidence for dark energy. And I don't know how many of you are familiar speaking with sigma 3, sigma 5, sigma, but in terms of probability, it was close to 100 sigma. Probability, I think it's 99 point, I think 259s. This is some insane, strong probability that dark energy is there versus zero dark energy. So for sure, something like dark energy is there. Now, what it is the universe accelerating? Is it just appear to be? Now we can debate all day long, but for absolutely sure, basically dark energy is there, and that's just an interpretation. So that ship has sailed a long time ago that supernovae may be wrong. Whatever, we don't depend on supernovae anymore to claim dark energy. Yes?
Is dark energy a singularity in there that would change some former understanding of the total energy in the universe once you found dark energy?
Yeah, so the total energy in the universe, is it important? That's not something that's directly useful to us, but you can calculate it for fun. And now you have to say because the universe may be actually infinite in volume, so you have to say in the observable part of the universe, in our Hubble volume, that's finite, you can multiply the volume by energy density and you can get energy. But that thing in its own right is something we do for fun, but doesn't infer our knowledge directly, just the energy in the universe. It's some number, and we're not sure. This energy density that I talked about, how it evolves per time, is what we're interested in because that's much more directly tied into physics. So this graph, whether this energy density is exactly flat or slightly increasing or slightly decreasing, we know it's for sure not like that. But that's at the forefront of research, and that's the thing one of the things we are trying to measure now accurately. By the way, all the data so far are this is a standard model in which dark energy density is exactly constant in time. But that's just a standard model. Yes?
Sort of related to that is the idea of the conservation.
Yeah.
So if you have something where the universe is expanding, now
Yeah.
the energy there, did something else lose energy?
Yeah, it didn't. And this thing makes no more sense to me than it makes to you. So I can't help you here or can myself. In general relativity, my more theoretical friends than I am, because I deal with a lot of data, they tell me it's perfectly allowed to have energy is not conserved in general in the way we are taught in physics 140 here. And it's just the case, and this technical statement is there's no time invariant killing vector or something like that. So and so I think intuitive explanation is that you can generate energy out of empty space, and it's not conserved. It's simply not. You're not borrowing from anything. It's just not conserved. You are getting more and more energy. But this similar, as I said, the speed of light is maximum. Well, yeah, if you go far away, it appears to be bigger. So it's one of those global things that are not the same intuition as our local everyday intuition. Okay, so in addition to dark energy, before I talk about DESI, I have a breaking news here. Breaking news is like 5-10 years ago, but it continues. This is, to me, the single most interesting development in cosmology since dark energy. It's called Hubble tension, and all cosmologists are talking about it for about 5, 6, 7 years. And here's what's happening. Remember, Hubble constant is 70. So Hubble measured 500, but now it's 70. And so actually, there are measurements that say it's about 74, and measurements that say it's 67. These measurements come from a very similar measurement as the kind of Edwin Hubble did. So Hubble did this distance ladder, and I didn't talk about it. That's another talk, but he had nearby measurements of distance in the solar system and beyond, then Cepheids, and then other objects eventually tap on a supernovae. So this is a distance ladder. This is traditional astronomical thing, modern version. The answer is 74. You've all seen this picture of the CMB. Some people call it cosmological Rosetta Stone. It's something you look at and you find wonderful things, including the Hubble constant at 67. Well, you would say, yeah, very good. I did say it was 70, and here we have 74 and 67. So that all fits great. Except if you plot the error, if I tell you the error bars, plus minus 1.4, and this one is very precise, plus minus 0.4. And if you ask yourself, well, how far away are these? They are very far apart. So if you like statistics, you can add them in quadrature, measure this distance, and you find that they're actually very far apart. In fact, they are far apart at 5 sigma. And I will spare you from sigmas again. They are far apart at this confidence. This is a confidence at which these two numbers disagree, because the error bars are pretty small. Now, one might say, well, okay, obviously one is wrong. Now, this is a gold-plated child of cosmology saying this is wrong. You don't do that every day. It's been checked out. It's quite robust. There's also other kinds of measurements that point to 67. So this value is considered to be pretty robust as a measurement. This is a little bit just robust just because, no offense to astronomy, it's an astronomical, it's an empirical thing. This is latter. There always could be systematics. But the leader of this team, Adam Rees, not only does he have a Nobel Prize, lots of people have a Nobel Prize, but he's one of the rare Nobel Prize winners who remained extremely active and on the ball, and he's coding stuff himself. He actually doesn't attend any meetings or is not part of societies and all this. He's at home coding, answering, kind of addressing criticisms. So he and his team are doing a very, very careful analysis in a bunch of papers that are very, very highly cited. And I read some of those papers cover to cover. That's an impressive analysis. So they have a big error budget and they say, look, we relax any one of these. Tell me what they would say this, tell me what you want me to change your analysis and I'll do it. And they always get some kind of this answer. So this is, we physicists and cosmologists, we like this kind of discrepancies because they might be signatures of new physics. So people are pretty excited. To me, this is the number one thing happening in cosmology right now in terms of potential discoveries. Sure, maybe there's an error bar in one of these two, maybe this one, but maybe it's a signature of new physics. What physics? Well, there were about 1,000 papers, literally, written so far on possible explanations for this, and none of them are compelling. It's surprisingly hard to make these two measurements agree. So the general idea is I have some new theoretical model, extended theory, in which you would find that these two agree. It's just that we are using obsolete theory where they disagree. And that's turned out to be quite hard. So we are motivated by Hubble tension. Any questions about Hubble tension? Well, obviously, I would never drop this. So I have money here, but I'm very curious what's happening here in that case. But if I have to pick one, obviously I pick this one, because that's, yeah.
It seems like on the first one, the 7.4, it's pretty obvious, just measurements. Can you sort of outline, how do you make that inference from the isotropy, so the cosmic background? How do you get to that?
Yeah, very good. How does Hubble constant show up here? So for some cosmological things, we have intuitive explanations that require a little bit of physics. So they take a few minutes to explain how some parameter, what does it do to the power spectrum? But Hubble constant, we don't have one. It's just a derived parameter. I can't tell you have more blue points or more red points or bigger blotches in this map. It's nothing simple like that. It just turns out to be well measured for reasons that are subtle. So I don't have a good explanation for that. It's not easy to intuitively. It's just a derived parameter. It turns out the structure depends on this, but in a way that's not apparent. It's not like, the blue splotches are bigger or something if you change it. No, it's not that simple. So yeah, but good question. Okay, so for the last part, so what are we doing now? All right, so there's experiments around the world to do dark energy, and photometric surveys take images, spectroscopic take spectra. There are famous space missions, Euclid and Roman, and all of these, they either had DE in their name, like DES and DESI, or else they are, the original reason for literally all of these was dark energy. And even things like LSST and the Roman space, sorry, LSST is here. Oh, I lost LSST, oh my God. No, here it is. Vera Rubin telescope LSST, that was originally built for dark energy. I can tell you the history of that. That's famous now for all of astronomy, but dark energy was original. Both of these were dark energy for sure. That's how they were motivated, and now they do a lot of other things. I'm going to talk about one of them, that not only are we involved now, but it's happening right now. So dark energy, so this is a fun picture. These are real dark energy spectroscopic instrument DESI. We are here, we are looking out in the sky. The color is a little bit false, but the galaxies are real. This is a small section, small part of galaxies from DESI year 1. Again, looking out, you look at larger distances and larger redshift. So this is redshift 0, this is redshift of like 1, 2, or 3. This is real data from DESI. Not like a simulation, nothing like that. So DESI, dark energy spectroscopic instrument, is located at 4-meter Mayal telescope at Kitt Peak. And you probably would have heard of this more than I did, because this was new to me. Now, here's what my astronomy friends tell me. The telescope is not spectacular. It's been built in 1972, excellent year, because I was born in that year. So it's a pretty old telescope, Nothing fancy, nothing huge, 4-meter. But what is special about this is the new instrumentation that was put on it. So instrumentation is special. The telescope is it is a dominant telescope on Kitt Peak. International team now has almost 1,000 scientists from 72 institutions around the world. And University of Michigan, Greg Tarley's group did a very major contribution to this, which I'm going to talk about in a moment. I try not to use hyperbole too much. I often get not super happy about how some survey is going. There's lots of negative things, but this one, in all honesty, data look amazing. And both data collected so far, and I think astronomy audience might appreciate that we get up to 100,000 spectra per night, up to 100,000. So that's and every night. So in fact, in the first month of operation, DESI collected as many spectra as all observations of all time. Of all telescopes, just in the first month. So, and I'm going to tell you in a moment how it does it. And it is truly the world's leading spectroscopic survey. Again, not because of the best telescope, but because of the best instrumentation and some of the people who worked around that instrumentation. And again, to remind you, what are we doing? We are looking at the 3-dimensional distribution of galaxies. So these are real galaxies, and they are test particles for us. And we are looking, you can see this fundamentally structure. We are looking at the overall structure as a function of cosmic time, but especially for one feature I'm going to talk about. Now, again, this is all secondhand information because I'm a theorist, but I'm told this is the DESI, this is inside the DESI, inside Mayal. And this is some of that new instrumentation I mentioned, especially the spectrographs, and very much especially 5,000 positioners, which are here. So sorry, I can't point to you and tell you what's what, because I would just embarrass myself. I'm not, not my strong suit, but I will talk about these fiber positioners. So these there's going to be a little movie played here. There are 5,000 little sticks called fiber positioners, and they each look at the sky, and they each take spectrum of a galaxy. So about half an hour, they take spectrum of a galaxy, they go bzzz. Each one of them moves, make sure it doesn't collide with any other one. Then they take another spectrum, half an hour later, another. And so 5,000 by 5,000, we get tens of millions of spectra. So that's how you get to tens of millions. You can't do one by one. You have to do 5,000 by 5,000. And this is done by Professor Greg Tarley. He retired recently. He lives in Hawaii now because he likes Hawaii, but he's very involved with DESI still. And that was absolutely phenomenal work that he and research scientist Mike Shubnell and their team, they built it literally where my office is on the 3rd floor of what's called the Neal Building, formerly New Randall. 2 or 3 doors from me, they have a lab, and they had these temporary workers they were assembling. And the experimentalist, I asked them, how do you know what to do? Where's the manual what to do, how to invent new things? Well, experimentalists have their way. But I'm also told this is one of the relatively few instances where a university group builds something significant, because most of the time these days it goes to national laboratories. And so this is maybe one of the relatively few remaining university efforts. So this is our claim to fame at Michigan, not anything I've done, but my colleagues who build, this is essential to get those redshifts. And that's been working very well. And the picture is, so back to some cartoonish picture, you go from, you're here, sorry for the bad resolution here, but we are measuring spectra of several kinds of galaxies. And sorry for the acronyms now. Brightest galaxies, BCGs, brightest galaxies at redshift, they're called bright galaxies. Then what's called luminous red galaxies, LRGs. We'll have millions of those in this range of distances and redshifts. And then we're going to have emission line galaxies, ELGs. I'm going to be coming back to these acronyms. And then we're going to have quasars, QSOs, the quasars, which are objects. In addition to them, we have a Lyman alpha forest, which is a different beast, which I won't have a chance to talk about. So we call these things tracers. They're tracers of large scale structure, basically different kinds of galaxies and quasars, and this other thing I won't talk about. And they kind of come in and come out in different redshift ranges. This is the now obsolete picture of our observations. You know how observations fill out. This is a galactic plane, and the redder this gets, I think, the more coverage we have. So eventually we'll have a coverage of 15,000 square degrees in the galactic north and south, a little bit of the south. This is the team, mostly my team, with a few others, and we got very involved with DESI. We got generously, I would say, funded by Department of Energy, and that was great because we could go out. Postdocs, Wendert Andrade and Johannes Lange, some of them moved on. There are some new students since, graduate students, postdocs that work with Camille Avestruz. These three were my postdocs, grad students. So it's great to have a big team. Everyone's doing something. You can see what they're doing. Let me ask one thing. Can anyone guess what I mean by blinding? There's a Wendert is doing blinding.
Make sure that the other team members don't know.
So blinding is something that particle physicists have started in the 1970s. You blind the analysis, that is to say, you cover the final result up until the very end when you have an unblinding event. And after that, you're not supposed to touch it. So all the tweaks in your analysis, you hide from yourself and from others before you think you do all the testing, all the tweaks in the analysis, all the assumptions, a million things, and then you freeze, and then you actually have a party and unblinding event. Why do we do that? We don't do that because we think some of us are dishonest. Maybe some are, but usually not. The reason is that your brain is stronger than you. It'll bias you. So even if you know from experience, if you're doing homework in school, and if 3 people got some answer, if you get a different answer, of course you'll think I must have done something wrong. Let me try again. But if you don't have access to see what they've done, then you'll say, oh, this must be good. Let me move on. So even if you decide I'm going to be completely honest, your brain will defeat you. It will bias you to agree or disagree or whatever in what you are supposed to be finding, even if you try so hard. So this was discovered by particle physicists in the 1970s, and it turns out you have to blind. And this is the first major big experiment that's blind, first spectroscopic analysis. There were other observations before, but nobody blinded in cosmology. So now this is not the very first blinding in cosmology, but the first blinding on this scale. So this postdoc is actually coordinating all of the blinding, which is considered a pretty big deal. So that's a very interesting thing. You have to blind. And if you don't think you have, I can convince you, you really have to. There were these historical measurements of the Hubble constant, and maybe you've seen them over the years, and it's one value, because they're all agreeing with the previous. And then they jump because somebody finally, and then same, and then jump. So that's all indication that you have to blind. So that's one thing to highlight. Now, in the remaining few minutes, a little bit more technical. I'll go through it at some pace. I want to describe what this workhorse is, baryon acoustic oscillations, and then I'll wrap up. So a little bit more, I'll have a couple of graphs, maybe even an equation with an integral. I'll describe what this is. But if this is confusing, don't worry, I'll give you a big picture. So this is a feature that we use. It's called baryon acoustic oscillations. And it turns out that in the clustering of galaxies, if this is us, it turns out that there's a special feature, almost like a ruler, except it's not a physical thing, in the clustering. And here's a big picture. Imagine you measure angle. You measure angle of some feature at some distance. So from simple, not even trigonometry, from simple geometry, if you measure angle, you can get ratio of this to this. And if you somehow know this, then you get the distance. So we measure distance to galaxies. There's a bunch of galaxies. And in these galaxies, there's a feature called sound horizon. So that's a little bit of theory. I'm going to explain the next few slides what this is. But for the moment, just agree with me that if I measure typical angle at which I see this feature, if I know the feature, I can get the distance. Hopefully that makes sense. Okay, so what is this? That's $1 million. What is this sound horizon? In the same great year when I was born, that was discussed for the first time, Sunyaev Zeldovich, 1972. So sound horizon is, here's a feature. So this is in normal language. This is a clustering of galaxies as a function of typical separation, we call the scale. So separation is measured in megaparsecs. Remember, megaparsec is 3 million light years. So on these scales, it's some function that would be something boring, except it has this obvious peak, and it's multiplied by r squared to accentuate this peak. So this is called a baryon acoustic oscillation. The reason it's plural in the original is it's single oscillation in real space is multiple oscillations in Fourier space. So don't worry about Fourier, but in case you're wondering why it's plural because we often talk about it in Fourier space, but in real space, it's just one bump. So I still haven't told you why this happens. I just told you that this is expected to happen, and that what we are measuring, interested in measuring is at what angle do we observe it. So what is this baryon, or what is this baryon? So it has to do with this sound horizon. Remember, so I told you we are measuring this angle, and I mentioned the angle, but now I'm going to explain what this is. So this has to do with a cosmic sound. I'm going to run a movie. This is at the Big Bang. This is a little bit of a cartoon. It's the sound that propagates at the distance that the cosmic sound propagates between the Big Bang and the present day. Now, how does it sound when in space you can't hear anything? Well, it's not literally this kind of sound, but it's a pressure propagation. Now, remember that the reason you can hear me is that air molecules are doing this, right? That's why you can hear me. I say something and then I disturb them and then they get to you. In empty space, you can't hear anyone literally, but there's still pressure. There's still particles, there's pressure, and pressure moves much faster, close to the speed of light. Actually, speed of light, a little bit less than the speed of light, not exactly. But it turns out that this is the distance. So you can see I'm talking about a much more theoretical thing. It's a distance light can propagate between Big Bang and today. The sound can propagate. And not to scare away the audience, but this is the integral. So it's my point here is not what's inside this formula. My point is it's a formula. If the formula means it's not an empirical relation. It's not, oh, I don't know, bigger galaxies have more stars or something kind of hand-wavy. It's an exact physical thing. So if you need to know certain things, you can calculate this thing exactly. So that's the whole point. This is a very firm footing because it's a formula. And details don't even matter. That means we are able to predict it. And so we get that. Almost with no error. So it does depend on cosmological prep. This is the amount of baryons. This is the amount of photons. This is a scale factor of the universe. This is the speed of light. This is a speed of sound propagation is speed of light divided by square root of 3. So there are some details. So the punchline is it's a formula. It's considered to be very, very robust. So here's again that similar picture. This is the same as I've heard before. You're measuring the triangle. It's sometimes called a cosmic ruler. It's called a ruler because it can be known very well. So that's at sun horizon. We measure that angle and we get the distance. So that, again, that feature corresponds to, let me just remind you, extra probability for galaxies having a pair, having a partner 100 of these megaparsecs away. I think 150 megaparsecs. I say on this scale, it's 100 because the units are a little different. So if I imagine I sit on one galaxy and ask, going away from it, what's the probability of finding another? It's some falling function, except 100 away, there's a bump. There's an excess probability, and then it keeps falling. So the intuitive, this is a very nice picture thing where we can have an intuitive picture. It's like you imagine these rings. We don't literally observe rings, but just imagine for every galaxy, there's an excess probability for having neighbors that distance away. So we are really measuring the size of this thing, except you don't literally see rings in the sky. You can't see them by eye. They are hidden, so you have to do analysis. Okay, so I did say this is going to get a little bit more complicated. But the main things are that this is considered in cosmology to be very robust because this sound horizon can be robustly determined. And so when we do that measurement, we get information on dark energy. So we have let me skip this. Why do I have this repeated? So cosmological results. So we have those tracers, if you remember, bright galaxies. And actually, it turns out we have two kinds of distances. So that's the one thing that I needed to tell you. I didn't. Because I talked about this, you can look, I'm going to wave my hands. You can look for galaxy pairs this way, but you can look at them this way. So we get this distance and we get that. We get two kinds of distances. And actually, to make our lives complicated, we don't literally do those. We do, if you don't look at the y-axis here, because it's a little bit different, just think of this as two kinds of distances, okay? So, and this is supposed to show this is actually one combination of those two, and this is their ratio. But if you look at this is bright galaxies that are lower redshift, it turns out we get the measurement only on one of these distances, not the other, for reasons that are not super important. This is literally the feature we measure. And in space of some two parameters, we get a constraint. It doesn't matter too much what the parameters are. And then you go to luminous red galaxies, you get more. And you go to another bin with combination of luminous red galaxies and mission line galaxies. You get measurements of the two distances, and you get another contour in this space. Because we have all these tracers, then you look at emission line galaxies in their own right. They have higher redshift. Then you look at quasars. And then you look at this thing I didn't have time to talk about, which is Lyman alpha forest. And once you combine them all, and don't worry what these parameters are. You get a combined constraint, and you can see the complementarity of these curves. They all combine to give you a constraint right here. So I've been in cosmology for 25, 30 years. I've never quite seen anything like this. This is considered to be very impressive that they complement each other and break what we call degeneracy. They trace out long curves, but they break out. And I didn't tell you exactly what these parameters are, but it doesn't matter too much for the moment. I'm going to move on just to say that we have a lot of different tracers complement each other very well. So these are our measurements that we publicized in April. So I'm going to flash two results, Hubble constant and dark energy, and then that's it. Then I'll take some questions. So the first, so we have, just to recapitulate, we have these, from this triangle thing, sound horizon, all that, we get measurements of distance. And then those measurements of distance, we convert into constraints on all kinds of things, including Hubble constant and dark energy. So for Hubble constant, this is our measurement. So first, remember that this CMB measured 67, and distance letter measures 73, 74. Here it looks more like 73, depends on which one. This is our measurement from DESI. So DESI alone, actually, with a little bit of a help here, I can explain what these things mean, but it doesn't matter too much. We get something like 68-ish. So we agree with lower values favored by CMB and obviously disagree with the distance letter. And this is our number, 6852 plus minus. So you can say it's a 1% measurement of the Hubble constant just from DESI first year. We are consistent with CMB measurements. Does this resolve Hubble tension? It does not. It just weighs, it puts more weight behind this as the global value. But it might be a physical reason why these local measurements disagree. So the Hubble's tension definitely stays. And then the next thing I'm going to talk about is dark energy. Now for dark energy, apologies, I'll introduce some parameters again. So the way we measure dark energy, we have parameters. And these two parameters describe what's called equation of state of dark energy. I won't explain it except to say that the standard model with cosmological constant with vacuum energy is right here. So standard model has this function exactly -1. That means this number is -1 and this number is 0. This is a scale factor that's a function of time. So -1 and 0 is right here. So this is a standard model of dark energy, and ruling it out would be, dark energy is for sure there. But now how does it scale with time? How does energy density scale is a question, and this is a standard model. So you can see that DESI data alone seem to pull away from it, but not a ton, because this is what I worked on in my PhD studies, understanding this. This is a very challenging parameter space to constrain. Very, very challenging. You just have to trust me on that. Very challenging. And then so DESI seems to show some preference for basically being in this quadrant. Okay. Then you combine it with the information from cosmic microwave background. You get the pink curve. And then you combine with supernovae. Now, supernovae, there are 3 alternative data sets. So you can get either the blue curve or the orange curve if you alternatively combine with another, or the green curve if you combine with yet another supernova data set, if you combine DESI and data set alone without CMB. So just to clean up this picture, if you now combine everything except you still have a choice of 3. If you combine DESI and these other pieces of information, you get this blue curve, or alternatively for the other choice, this curve, or alternatively for the third choice. These are 3 teams with 3 different kinds of supernova data sets, while these are unchanged. And you can see in each one of these cases, we are away from this point. Now, how far away? That's a statistical question. Again, we measure things in sigmas. This is 2.5, 3.5, 3.9 sigma. 3 sigma is 99.7%. And at least to me, that's when I get excited. If something is less than 99.7, it kind of happens a lot. But 99.7 is, and you can see 2 of these 3 are more than 3 sigma away. So therefore, we are seeing tantalizing hints for departure from the simplest model with the vacuum energy or the cosmological constant. This news was relayed. I think there were 400 articles in the world about this after DESI came out. It got a lot of publicity, mainly for this result. And I say with a good reason. This is interesting, because seeing departure here would be yet another surprise for dark energy. What's next? So next week is actually pretty big because on Tuesday there will be a release of, remember there's a BAO feature, there's more than the BAO feature. So there's a whole pattern of clustering, what we call full shape. That's a lot more complicated analysis. And there, by the way, DESI, there are hundreds of papers. I'm just talking about one or two that are the most interesting. So this is the thing also I co-coordinated. A big analysis. This paper will have several hundred people. It's going to be publicized on Tuesday. I don't remember when embargo ends. I can't tell you what it finds, but you'll see there are some results. What I'm really interested about is year 3. So this 3 years of data, results will be out in the first half of next year. And that's supposed to have a major improvement in precision. This, I can't tell you if it's major or not major. Maybe it's not as major, but this is going to be a major improvement in precision. Beyond that, 5 years of DESI, we'll have 40 million of these tracers. Then beyond that, we will be working on DESI 2, which will be same telescope, I think same instrumentation, but more galaxies. And then this is going to be around the time I probably will have retired by then, but who knows. National agencies have actually recently recommended that something called Stage 5 spectroscopic survey, which is the next generation of DESI-like thing, maybe at a new telescope, better, more and better of everything. That's a little bit depressing in 2030s, but that's when it takes a while to collect money and expertise and to do it. So in conclusion, dark energy is for sure there. Universe is expanding faster and faster. We don't know why. Hubble tension is a big thing in cosmology. Two values of the Hubble, measurements of the Hubble constant disagree. We don't know why. And there's a potential for discovery there. And I talked about DESI survey and want to flag this is unsolicited mention, but I wrote a book on textbook on cosmology that's actually not super high level. Part of the reason I was motivated because there are some really technical readings out there, really like too technical for me. I'd like to read them and learn more. But this one is aimed at upper undergrad, maybe lower grad, tries to technical, but tries to explain things intuitively a little bit from scratch. So want to advertise that and maybe take a few questions at this point. Thank you all.
I'm intrigued by the neutrino masses maybe playing a role in this.
Yeah, good question. I didn't have a chance or time to talk about neutrino masses. I don't have a slide nearby, but we measure the sum of the neutrino masses. That's kind of a different talk, but we measure neutrino. We are sensitive to the sum of the masses of neutrinos, these very light particles, and we favor them to be very, very low. But we know mass cannot be 0 because neutrinos turned out to have mass from different kind of experiments, particle physics. We don't know what to make of it. I don't think anyone knows what to make of it, except we have very stringent constraints on the mass of neutrinos. Let me see if I can pull it up. Maybe not. Let me see this, that, maybe I get rid. I think I got rid of that slide. So yeah, so I don't know if you have any more specific. We are sensitive to massive neutrino masses, and we have quite stringent upper limits, and we'll see if we can. Right now, they're just upper limits. There's no detection of neutrino masses. So, yeah.
Your telescope in Arizona that you showed us, is that taking a photograph or the data from a different point of space or in time or both?
Both. Near me is close to me and now, and far away from me is, well, far and then. So here now or there then. And so as they specialize in different kinds of galaxies, and so it's interesting, we need, for spectroscopic survey, it turns out you need to know what you're looking at. And again, you guys might know this better than I. You can't just point spectrograph at the sky. You have to point at the galaxy. So we have these surveys that find galaxies for us. And then we point these 5,000 fibers at 5,000 of them at a time. And they're distributed in time/space. That is to say, some of them are far away and at earlier time in the universe, and others are closer to us and later time in the universe. The same is that when you look at the sun, you see it as it was 8 minutes ago, right? Not as it's now. So it's the same principle. And we work off of that lever arm, you know, the whole point is that we like to get the range from galaxies 1 billion years ago to galaxies 10 billion years ago. Yes,
How many fibers are there in the telescope?
5,000.
So our telescope, 24-inch Macbeth, was built to do spectroscopy on individual stars. I think like 2 or 3 spectra
see.
on that. Instead of 100,000.
I can't even appreciate this because I don't have this background. You really have to appreciate some things in life, you have to do it the other way. And yeah, so right.
1 or 2 spectra at the top.
Right. Yeah.
Unbelievable.
Yes.
Why do you think dark energy, just your own personal opinion?
Well,
So it's so lame.
There's no good, because in particle physics, if you think about physics, everything happens very early after the Big Bang at higher energies. There are normal particles, protons, electrons, all these particles have much higher masses than the effective mass of dark energy, so to speak. So nobody, including me, can make any sense of it. Is it some kind of phase? I mean, you asked the question earlier about inflation phase, and then nothing, and then second inflation, dark energy. Sure. But why is the scale 10 to the 60 times different between first and second? So this is, I don't even have a good guess here. I don't have so no particular. And this is, again, I don't recommend that question is like too hard, you know. It's not like why are we here question, but it's a pretty hard question, you know. To find an answer, theoretical explanation, but to measure properties of dark energy, for sure. I mean, I showed you that plane. We have all kinds of measurements and are getting better. And that's a challenging parameters, by the way. Those two are very challenging. Those two are the W0 and WA. Your comment on McMath and now spectra reminds me of a conversation of one of my cosmology colleagues, an astronomy professor. Because astronomy, this is also interesting, astronomy cosmology debate. He says, he asked Greg Tarley, Greg, why do you need, at the time it was 1 million, you know, why do you need millions spectra, 1 million galaxies? If you have 1,000 galaxies, you've seen every kind of galaxy there is. Why do you need 1 million? That's a good point. And the answer is, that was Greg Tarley and Doug Richstone. So Doug said, why do you need? And the answer I would have given is because with 1 million, you can do the statistics that you cannot do with 1,000. I mean, it's really crappy statistics with 1,000, but 1 million and 10 million, you can do these precision statistics measurements that are more in the realm of cosmology. So it's interesting how both sides are kind of right in their own way. It's true, you've seen every shape of a galaxy with 1,000, but you need millions to do the statistics.
Yes. Any questions from the Zoom audience? Anybody who do have a message in chat here? And that is. Oh. That was just saying the audio and video on the Zoom audience was great.
Oh, okay.
Okay, one more question.
Thank you, guys. Thank you so much. Pleasure is all mine. Thank you.
A small token of our appreciation.
Oh,
Present you with a.
thank you.
official-
Oh my God, look at that. Thank you. This is really nice. Really nice. Thank you. I will wear it happily outside, including when the weather gets a bit warmer.
I'm gonna wait just so there's some people on it. So-
But it sounds like these acoustics periodic fluctuations.
That was a long different scale. That's so initially the effect was so small. The effect didn't happen. You know, you have to have those orders of magnitude change before it becomes permanent, right?
Because how is from the. Yeah.
So then the density should. So right after that extent, density should be approximately the same.
To me, no, this thing is good.
They don't have energy and stuff.
Periodic oscillations. It sounds like we can.
Yeah.
All right. We got two things, you know. First one is Jim, the forester, has once again been so kind as to produce a proposal to one off next year. He actually was the main on. He was situation, I think, was everyone. But anyway, what's happening, Jim?
I never had a chance.
Yeah. So anyway, I'll kind of take it slow so you can rejoin us here. But this is what we had come up with. The open house dates. There, you know, there's some that are highlighted here. The reason for April 5th is I believe in that case, we were not proposing an open house, but a possible thing we did like at DNR the library last summer, we did that one night. It just happens that April 5th, though, we're gonna have the movement marks actually quite close to each other. So it kind of adds a little bit to it. And we would probably have it at the district library again, so that's why we got that as something to consider. Then the open house days to consider was April 26th. And then May 3rd was another option for something at AEO. Maybe Jim remembers which one was actually maybe better. If either one of them was, probably the phase. There it is. Perfect timing, Jim. Can you remember exactly why we had proposed April 5th or May 3rd for that moving march second library?
Those were dates that I came up with.
Yeah.
And those dates, those two were very close to one another. So it kind of made sense that we would be out there. So both of them were once, and Brian thinks that there may be some free listing out of those conjunctions.
Right.
That, you know, if people know that we're gonna be out there, I've already heard from watching the weather on Channel 4 or whatever, that this was happening.
That's what it was. We had two of them, yeah. So one was sort of a backup, basically. But we could potentially do both, was the
We could
idea.
potentially do both. There'd be no reason not to, other than we don't have enough people to be out
Yeah.
there.
Jim,
3rd is commencement,
which is,
May 3rd.
oh. Well,
That could either mean you've got a huge
I was
audience.
gonna say that could be good or bad.
Yeah.
But that is duly noted.
Although people in the bars that night, so there will
That's
be.
true. Maybe
folks
that's a
out
good thing, actually, yeah.
These are gonna be held downtown.
I guess we should ask Amy about it.
Yeah.
She knew we were talking
there.
about this.
We're
She didn't chat.
a few months out, so I think we can talk to the library about it. We just have to decide whether we want to.
Right,
And this is gonna be held downtown at the library.
that was our idea, yeah.
I remember
strong.
a few years ago, we had one at the Oak Valley branch, right, and that had a huge,
Yeah, never know.
maybe easier for people to get to, easier parking.
Yeah,
Well, that Yeah, there were quite a few people out there to look at the planets, because Mars was pretty close.
Then years ago, we did some on, what was that, First Street? Ashley, yes, on Ashley, right next to the parking lot there, because you got a really good western horizon.
We've been
Well,
out
that
there
may
several
there
times
may
over
have
the
been.
years, it was
Yeah.
partial.
We
Solar
usually get quite a few
eclipse,
people there too.
comets.
Yeah, yeah. I think we did one piece. No,
Venus transits were a lesson.
yeah, you're right, and, top of Angel Hall,
Yeah,
yeah.
All of those skylines changed a bit now, so it's hard to say what's good or bad.
And I think that library worked pretty well, so,
yeah, we had quite a few people stop and look through these.
yeah, yeah. Well, okay, so I guess the idea is we keep both of those there.
It'll depend on what the library has to say about it.
Depending on that, yes, correct. So we'll see how that part goes. Does anybody see anything wrong with April 26th, that would be a regular beach open house? Then we had May 24th and 31st, Jim and Billy the 31st. Was
We'll
that
be
like
up
the
a good-
first fuller moon or?
It's not that. It's earlier in the cycle than that, but it's still the moon is gonna be up like past that time.
Now, were you thinking the open houses, 24th and 31st?
Yeah, those are open, those are the open houses closest to the new moon and. New moon is, in May is pretty close to the 24th, and so the 31st is like, you know, day 5 or so of.
Might be a busy May for us. Okay, then, we got June 21 and 28. You notice all these tend to be a little later in the month. I think last year they were changed.
Yeah, it was.
July 19 and 26, August 16 and 23rd. We were looking at September 20th and maybe the 27th. But we have, confirmed that AATB is gonna be the 26th, 27th, so that's why I scratched 27th. So that would be September 30th, and then we conclude October 18th. Now, if we really wanted to go crazy, there's some other dates we could inject in there. Being March 22 and 29. Would one of those be a escape there?
Well, there, the 22nd is the primary date. The thing with the 22nd is moonrise in the early morning, making it difficult to see things like M30. Of course, it's always a problem seeing those objects in Capricorn anyway. The very soft Sagittarius, those are big parts. This the marathon, the 29th is the alternate thing. 22nd is clouded out. The 29th, the early objects are rotated more into the sunset, so it's like 74 and 77. Probably couldn't pick out of the
My thinking is, without any of those, we've got, I come under 13 potential events. Also consider there's gonna be AATV, which is possibly 2 nights. And then other thing we don't know yet is how many other people are gonna request events, and they prefer also Saturday night or Friday night. I know what was one of them canceled for sure. It's gonna request something. Spring was Western Library. Yeah. And I'm sure that's not gonna be the only one. So it probably would be a bad idea.
As they asked about someone to try to get.
They want to win it, okay.
Yeah.
I think we make it known that we're keeping the Friday nights open
Yeah.
the requests from other institutions, so that might help.
Right. Well, as far as March, should we maybe say those are just messy air, not necessarily open house.
That would
See
be
how it
fine with me,
works.
it's, I think 2016 is the last time. The weather, aligns for us along with other factors that prevented us from getting out there.
October 25th, that would just be an additional October. October's usually a good month, weather-wise.
What's this year's?
Yeah, oh, definitely. And I want to see stuff right at the beginning of it, see how everything up. What do you think should be at that? Or are we pushing it too far?
I'm always willing to go out there.
Yeah,
You know, it has to be more than just.
that's
usual
true. We always have
suspects,
the option of canceling if we go down.
because,
If
you
not
know, the usual suspects are getting to be quite gray.
Yeah.
And, you know, one or two of them get sick and there's,
Right,
or somebody in their immediate orbit gets sick.
yeah. Yeah. So, should we put it in there then, to see how it goes?
Yeah, we can do that, sure.
Then November, my thinking on the 22nd, oh, Thanksgiving's 22nd, okay. We still don't need November this year. Right on.
We didn't schedule any sort of November this year.
Really depends on the weather, right? Accessibility.
Usually the weather is not good in November, that's one of the reasons we sometimes don't schedule.
You know, it's true, since I've been in the club, we've maybe had 2 or 3 things come off after the middle of November.
Yeah, sounds about right.
And, you know, before the spring. So. I really don't recommend late November.
Yeah, I'm wondering if maybe we should not be November at all. And if that maybe some more open days for some other entities. Possible. Of course, there's a good chance we'll have to cancel, that's what happened in Westland. Yeah.
I think if we have something happen on the 25th. An anomaly. October 20th.
What about
I think October 25th.
Yeah.
Most years is when you approach Halloween,
Oh,
aren't bright and sunny during the day and clear.
that's true. So. Maybe we just add 15 then, in case we don't get lucky with 25th, maybe 15 once.
I
Just said you could always cancel.
True. Both of them, that's what you think?
I would go with the November 5th, the 25th and November 15th, not 22nd. I think that's pushing them off.
Yeah. So you're thinking this,
Not the 22nd.
oh, not the 27th.
The 5th, not.
Cross out the
Oh, I
road.
crossed out. Okay,
Keep the 15th, drop the 22nd, there you go. All right, and we say that's the thing, but the 15th is questionable, right? And October could be questionable, we're not doing, it depends on the weather.
anything after the middle of October is questionable, but. You know,
Right.
we've,
But you never
before
know.
Halloween, we've had good luck. Relative. Between 25% and 50% instead of 5.
Then there was the infamous landings November years ago, remember that one?
Oh, yeah, where.
All
it was
excited,
clear.
yeah, supposed to have an excellent landed meteor shower, and we had a beautiful day. Not a cloud in the sky all day, it was very unusually warm, we thought, how lucky could we get? And there were people going all over the place, a whole bunch of us went up to Beach Mountain, and we're getting all ready, it starts to get dark, and fog rolled in the middle of the whole damn thing. The next thing you know, we had club members literally scattering everywhere, going up on the thumb up north. Dave and I went up in the middle of the night up to my parents, in fact, the Flint area, Scorched Creek, but we got out of the clouds and we did see something. But that was just, it was hell getting home though, wasn't it?
Yeah, I went north, with Shiawassee. So
Yeah,
I think the only place that had a good night was, the EMU station, Fish Lake.
oh, right, yeah.
By the time we got there, I remember, we had a very large crowd at, Hudson Mills.
Yeah, there was a lot of people there and
Yeah,
just,
that was just.
you know, at 8 o'clock, boom, just.
Yeah,
So,
that was so neat. I still haven't got over that.
I guess not, Charlie.
The therapy hasn't worked.
Yeah.
All right, so do we go with this? That's all I can clean it up and send it
Yeah,
out.
that's fine with me. I would,
Okay,
before we finalize this, I would count up the dates that we're committing to for, you know, public events on our own behalf, see what that number, total
Yeah.
number is.
thing is, we can't predict that, really.
Well, we don't know that they'll come off, but we are committing to them if they can. And last year, we only put 11 dates.
How did we do?
I can't remember how many of them we did, but on a couple of them, we were close to having to say, call them off, even though the weather was good.
Right,
Because we weren't sure we were gonna have enough numbers,
I almost think we did all one off.
not this year,
Just, maybe that's what I thought it was close, but
it was close.
yeah.
So I'm assuming that the Messier Marathon ones wouldn't be up.
No, they're not, those are numbers.
Yeah,
Oh, you know, we trekked out, last one was 8, 9 years ago, we trekked out to, Lake Hudson. Yeah, that was a great night. Barry got over 100.
wow,
So,
I shoot.
It was amazing. I mean, not a cloud in the sky all night. I was picking off objects in Sagittarius tree branches as the sun was coming.
Still counts.
It was good.
Okay. I'll check with Amy on those, AADO.
like I say, count up, see what total number we have
Oh, right now,
right now.
okay. Well, if we don't count the Messier Marathon, it's
We
1,
know.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's only 3 more than last year.
Yeah, that's true. The 2 moonlights at the library, you know, even if 1 or 2 of us shows up, that'll work.
Yeah, that's true too. Yeah, we don't need the huge turnout for that.
So we're talking about 12 actual. Right?
Okay, yeah.
11 last year, and one of them might, and we know a couple of them will have to do with weather, but still trying to get the commitments.
Years ago, Chris Sarnecki actually counted up the dates. We were supposed to be out there and the dates that had actually happened. Rarely did we go over 50%. I think 2009, we got to like 75%, and that's the most we've ever done. It's usually 50%.
I remember,
I think it's almost probably,
yeah, something.
yeah, should be our.
I remember Mark Press did kind of a problem like that too. He was looking, so we got joking around years ago about the full moon cloud causes the clouds to dissipate. So Mark, all this time, was actually charting all of this, and according to what he was reporting, it was actually true. There was a better chance of clear skies during a full moon, which is true for her. Okay, thank you. The other thing is we were talking about purchasing the Sea Star for purpose of going out to club members. I did confirm with Amy and Cantu that she would be willing to be the guardian of that telescope. And it's fortunate, she's got the library one, and she might have got one herself too. But I know she's operated the library one, so she would be able to tell somebody when they pick it up, you know, how to get started with it. They are, if you go to like High Point Scientific, $500. So it's over a threshold, which is required of both. And generally, we tend to be in favor. We've had some mixed feelings. Some of this I can understand because I'm partly there. We're a little concerned, maybe at the message we're sending out. Are we sort of like telling people forget optical, just go for astrophotography? And you've probably seen too how many new members have joined in their little intro thing. They want to just get in here and jump right into astrophotography like on day 2. But on the other hand, I guess I looked at it, I mean, I was sort of in that optical thing too, and I still am. But then I guess I'm looking at it, I'm trying to embrace both worlds really. I intend, for example, and I did that in fact, when we went down to Tecumseh. I brought the Sea Star down there, but I also brought an optical instrument. So I can show people either way. And I think in that sense, it's kind of cool because you can explain the difference and, you know, that kind of thing, so. But I guess it's just a matter of, whether you think we should do that or not. Any questions or?
Well, I think we should do it. I think this is a step toward getting a better instrument. Because there are much better ones out there.
Yeah.
That cost 8 times as much.
Oh, yeah, once you get beyond that, the price jumps immediately.
Yeah. But we're going to. We're going to think, if we're thinking about doing something with a better instrument, then we've got to start somewhere.
Right.
$500 is
Yeah.
a good place to start.
Exactly. Yeah, and if it turns out it's really not all that popular, then at least we didn't waste 1,500, 4,000.
I think it would be great. I think somebody, I think it's actually wrong.
Well, I noticed when we brought that up at the last meeting, somebody asked how many people in the room would actually check it out. I think 5 or 6 hands went up immediately. So.
Once you start on that, then we start asking questions about what did I just see in this stuff, how other things. But it's a way to get more people involved.
Yeah.
Now, I don't have any problems with this. Being up there for individuals who use their driveway or whatever. You know, we have to be a lot more careful with what we call our public events because. You know, dark adaptation matters a lot to people's safety on each.
Right.
It's a major reason that we still insist, even though the skies are so much degraded from what they were 20 years ago, that no white lights, because it's just a lot better for people to get around up there if they've got the night vision.
Right. Not like the Sea Star racing, like the app that you're running with dogs.
Yeah, yeah, and we've
Yeah.
managed to operate with astrophotographers up there before,
Right.
but you know, it is something that
Yeah, it's something.
we have to regulate.
Yeah.
So, April. If people pass, I usually direct them to the electronic telescopes first. Then the optical telescopes on the roof, and then the optical telescope at the dome, so that they're, when they first get up there, they're not dark down
Oh,
yet,
there you
they
go,
look at the
right.
pretty pictures. Then when they start to get a little more dark down with the small scopes, and then they're finally actually dark down to the So you can manage some of that safety issue.
Not to cloud the debate any further, but I was saying they just announced the Z30.
Hmm.
And so it's more compact, but
That's, yeah.
the claim is that the optics are faster, shorter focal length, wider field of view, better camera, better software. So supposedly available in the next few weeks, so it's $350, so that might be another option.
True. Then again, it's not like we have to save money. In fact, we really should spend some money before we end up having to.
You know, I don't think this fund is ever gonna have too much. Unless, you know,
I think there is an IRS limit for a C7 organization. If I remember, I forget what it is, but. I think there is something to that. That's done.
it's in the,
Yeah,
uh,
oh, it's that much.
per year. Not in the bank,
Oh, not, oh, right, so it's not assets, it's how much is.
yeah.
Okay.
Okay.
Really well, really.
But still, what are we gonna do with that money unless we do something like this? So
There's things to take care of, to.
Yeah. we've got plenty of push for that too.
Buy your own property.
Well, now that's getting there a little bit, yeah, now we're in fundraising. Then, of course, we gotta move the math out there. Well, okay, we prepared to vote, all in favor,
Who made
is
the
anybody
motion?
opposed? Cool,
I say Jim made the motion.
Sure,
oh. Yeah, did you wanna say you made it?
yeah, I made the motion.
Okay, then I guess I support it. Okay, thank you. It's a done deal, I will let Amy know, I think Doug is actually gonna buy it. If I remember right, he was gonna buy
Right,
it
he's
straight out of the
gonna order it.
treasury thing and have it shipped to Amy, if I remember right. We'll double check that, so.
We had to
Okay.
authorize and that will work out for.
Yeah, exactly,
That'd be the easiest way to do it.
yeah. Okay, I think out in the Zoom audience, we do have Brian on. Is he still there? Anything to report, Brian?
No, I have no report. Do you have any questions?
Put the screen up there. Isn't that the selector
That's
down
the
there?
overhead.
Thing on,
That's it's on the desk. Sure.
Oh, yeah, yeah.
There we go.
Okay, well, after all that, you said you had nothing, Brian?
I don't think that there's anything to report. I did offer to fill a speaker hole if one exists for next year.
Yeah, I was thinking about that. Should we just push it down for one, or do you want to be like a reserve, or?
I'm flexible. But I just need some advance warning.
Yeah.
It's a little far off though, right? Because we're talking about 2025.
Yeah, next year.
And we've got speakers up through March right now.
I have two lined up, but I haven't been able to tell them dates, so we have to, I'd like to get the list of what the current dates are. Could you send that to the officers?
Yeah, I can send it out. It's on Google Drive too.
I don't have that.
Oh,
I don't have access to that part.
yeah,
Yeah, probably, but like I said, I don't have access to it.
Okay.
That wasn't added in when I got it signed up.
okay, well, speaking of reports, Ken.
I do have two potential speakers lined up and, they're both repeats. One would be on the Dragonfly project, that's going to Titan. And the other is our, spectroscopy of the, around Jupiter. They were looking at the same speaker, Jeff. I have two of them that are available for next year. I just don't know when we can slot it. That's why I need to.
Yeah, gotcha.
Other than that, I don't have, I don't know anything else to.
Excellent. Okay, Doug, our treasurer was not able to attend, he would have been Zoom, of course, you know, in Traverse City, but he did send the officers a report. There were
You got that? Don't get
some
it.
numbers in it, yeah, I think we'll go right now. And Doug says we now have 212 members. And that's compared to 207 back in August. We spent $420.16 to replace the Argo Navis in the observatory. $45.04 went to Don Foley to replace the battery charger for the cave telescope. $1,150 to the Astronomical League for the purchase of 25 of those RASC calendar, or not calendars, observer guides for 2025. Oh, that includes, it's the calendars and handbooks.
Handbook.
That's what I tried to say, handbook, yeah. Also $250 to the International Dark Sky Association, which we do every year. $15.85 went to AT&T for our open house hotline. And $23.67 went to Amy for printing and mailing expenses for the newsletter. And he's received payments so far for 11 calendars and 12 handbooks. And you may have noticed he sent an email to the whole club earlier today saying he still got more calendars and handbooks. People want to reserve, so. That was Doug's report. Amy could not make it, neither could Jeff or Krishna, so that brings us last but not least, Jeff.
Okay, I'll make this quick. Some of you may remember we had a club member named Stuart Colin. And he was back in town, stopped over to see Tom Ryan. And Tom called me up and told me that Stuart Colin had donated a set of binoculars. They're made by Orion. They're 8 by 56, which means they have 8 power, but the field of view is 6 degrees instead of 5. And he wanted to donate them out to the observatory, which is fine because I'll take these out to the observatory, so what he donated. And then they are nice. I mean, there's nothing damaged or cracked or anything like that. And then we're out at the observatory next year. If there's people want to look at the sky with a pair of binoculars, they can use these, or they'll leave them out at the observatory. So I know there's been people at times before brought up binoculars there. And I think these of the 6-degree field of view would be a little different. Interesting looking. So that's the only real thing I have. I did turn on the heater on the observatory, so we're now heating up the observatory. The heater that we bought last year. And I did go out, get ready and shut everything down for the rest of the year because we're not going to be using it anymore. Other than that, that's all I have to report.
Thank you, Jack. And I think I remember reading a review years ago on those binoculars. And that was actually quite good, as I recall. They're supposed to be really nice.
Stuart, what was the last name?
Cohen, Cohen. Yeah, he was a member, man. I remember the name, a long time in the 80s now, when he was back in town again. Stopped and talked to Tom, and that's when he wanted to make the binoculars.
Does anybody have anything else? Jim?
We're, a couple of us were talking about this on the walk over here from the parking garage. It would be optimal if the website had the date of the next meeting right there.
Mm-hmm.
On the front page.
On the front, on the homepage. Or at least a button that would take you to the calendar directly rather than to have it pulled down and.
Yeah, it's a good idea.
Yeah.
For the next meeting, something about the next / current.
Okay.
Outcome.
Talking the old website or the
Either one.
Yeah, we're gonna send that off to Jeff. Also, earlier today, there was some email between Jeff and Doug Scoville. And apparently Doug noticed some things that. He thought could be improved too, but he wasn't real specific, but they said they were gonna talk and see what those things were. And then he also, his other thing was, he thought. That we didn't need the password for the members only section anymore. But Jeff thinks what it really is that once he signed in and went in there the first time, it simply remembers the password. And therefore it's not asking him anymore. In fact, he said a trick to it is if you look at the page and you see. Button or whatever, there, an ability to edit your profile, that means you're not logged in. Which is odd, it almost seems like it could be the other way, but I'll double check, I think he worded it the opposite of what you would think. But if you see the thing about editing the profile, that means you're not logged in, if, did I say that right? I think he said if you see it, you're not logged in, if you don't, you are. I'll see if I can get some clarification on that, anyway, it was interesting, so.
Most people's computers remember logins like that.
Yeah. That's why,
Seems like it usually asks.
It depends.
Yeah, I'll ask you if you want to remember it.
Yeah. Maybe there's some
That's
browser
what
settings.
mine is.
Yeah, that's what I always thought I'd seen. Yeah, no, anyway, they're gonna look into that, too. Jeff thinks that's what it is. Anything else?
One other thing. When we were driving over here, we were looking at the observer website. Our observer website. And while it listed the open house tonight here for the Detroit Observatory, it did not mention the logo. And Christine had submitted that saying this was a lowbrow event.
Yeah.
And so we thought that, and so we're not sure why it didn't appear on the website. And not certain that it appeared in print since we've got the print version with us. But we thought that we were getting our activities entered into the Observer website. So we need to find out what's going on.
Yeah. I always thought of the print edition, I never thought about their website.
Yeah, and I mean, we were just looking at that, we're trying to figure out what's going on downtown. Crowd is.
And it's interesting, it had the open house here,
Yeah.
but didn't mention logos. So it's like, well, there's two astronomy things that did mention.
Yeah. I guess the question is who would contact about that?
Well, I would talk to
The person
Michael
that.
Wright first.
Okay,
She'll send an email and see if we can find out.
yeah, so let us know if it doesn't go well, let us know, we'll get you. Okay, anything else? In that case, I will entertain a motion to adjourn. Here. That's a motion to adjourn. Thank you, everybody, I assume nobody objects. Okay, thank you much. Have a great Thanksgiving.
No.